So, when my parents asked me what I wanted to be when I grew up, I'm told that I answered that I wanted to either be an astronaut or a bricklayer. I'm pretty sure the bricklayer was because I thought that would be like playing huge Lego, which was clearly going to be awesome. The astronaut, I'm not so sure, but I think it was because I wanted to fly. You know, not in a plane or something like that, but with my body, like the astronauts appear to do up in their space capsules. I also remember a formative experience back when I was about 10 years old. We'd done a module on space, and not just like space, like planets and stars and stuff, but actually traveling to space. There was this special shuttle launch planned, and I must have been super excited about it because my parents agreed to wake me up at 3 a.m. in the morning so that we could watch the launch live. Now, this space shuttle launch was going to be special because for the first time ever, a normal person, a teacher, was going to be launched up into space. Now, I see a few of you can see where this one's going. So there I sat, an inspired 10-year-old, awake at 3 a.m., and I watched as the Challenger spacecraft blew up 1 minute and 13 seconds into launch. Going back and watching that footage again, more than 25 years later, still feels like a punch in the chest. It affected me so profoundly, and probably anybody who had seen it. Before that, I wanted to be an astronaut. After that, I really wanted to be an astronaut. Go figure. I think you could probably not have brought home in any stronger way the difficulty and the importance of that kind of endeavour than to show me people who were willing to risk their lives to try and achieve it. Well, I never became an astrophysicist or an astronaut, well, not yet anyway, but I may have done what I think might be the next best thing, and that's become an astrophysicist. So I don't get to travel to space, but I do get to study it, and I feel in a way like I never really have to grow up. So what I study is cosmology, the expansion of the universe, everything that there is out there, and the fundamental laws of physics that govern it. So I spend my days talking about things like dark energy and dark matter. You know, through astrophysics, we've discovered that only 5% of the universe is in a form that we know how to see and touch. About a quarter of the universe is made up of some sort of dark matter, which is the stuff that holds galaxies together, and the rest, the majority, is some sort of dark energy, which is accelerating the entire universe apart. That's what I try and figure out on a day-to-day basis. So I often get asked, what does it feel like to study space? You know, to stand down there and stare into the deep, dark depths of the cosmos, day in, day out. Well, and don't they say, doesn't it make you feel small? And I'm like, well, you know, sort of physically so. But hey, I'm as small compared to a galaxy as I am large compared to the nucleus of an atom, so I figure that I'm about Goldilocks size, right? Just right. And in another sense, it doesn't make me feel small at all, because thought, human intellect, has somehow encompassed this whole thing. Think about it. We've gone from a species who a few hundred years ago could barely really understand the world in front of our direct physical senses, to extending what our human body can do, our senses and our dexterity, to a point where we can measure what's happening in the nucleus of an atom, out to something as vast as the network of galaxies that make up our observable universe. That's not intimidating, that's empowering. Now, one of the most important things we've learned by studying the universe is that it tends to follow a sort of a strict set of rules. The same processes that we can watch going on in atoms here on Earth also happen in distant galaxies, and we can see those. The laws of physics appear to be the same both near and far, both in the present and in the past. And that's one of the most important things for life like us to exist, because if that was not the case, it would be pretty difficult for life to persist. Like, for example, if the charge on the electron were to change with time, and just randomly fluctuate, then our bodies would hold together one moment and disintegrate the next. So in that sense, the universe is sort of kind. I wouldn't necessarily say that it's been designed well for us, although that argument has been made, because you can imagine plenty of universes in which life would be impossible to exist. But I think we're very resourceful. We've evolved really well to cope with whatever the universe has thrown at us. For example, you could ask, why is it that we see in optical light when there's a whole spectrum of wavelengths that we could see in, all the way from gamma rays and X-rays out to radio waves? Well, it's because it's useful. If you look at what wavelengths actually get through our atmosphere, visible light is one of the few stuff that actually gets to the ground. Things like, ultraviolet gets blocked by the ozone layer and that kind of thing. You can also ask why we've evolved to be able to understand mathematics. And that may be because the universe obeys mathematical rules. So, the same physics that we need to understand where to move to catch a ball that's been thrown is the same physics that governs how planets orbit and that kind of thing. So our instinctive physics also governs all sorts of other things. Now, speaking about orbits of planets, I did actually eventually find out that the astronauts aren't actually flying, much to my disappointment. One of the first things you learn about gravity is that it doesn't stop when you leave Earth's atmosphere. So the astronauts aren't in zero gravity, it just looks like they're flying. And that's because they're actually falling at a rapid pace, but at the same pace as their spaceship. So in that sense, astronauts are really just extreme skydivers. They're hurtling towards the Earth. The only difference between them and skydivers is they're also moving sideways fast enough that they keep missing. That's all an orbit is. It's falling towards the Earth and missing. So anyway, I grew up on a Sydney beach, on Coogee, in the surf club and doing all of those sorts of things. And you learn a lot of physics by going to the beach, by understanding, the propagation of waves and those that hit you, to understanding the radiant energy from the sun that burns your skin, to understanding the power of persistence as soft water wears down hard rock. But one of the most important lessons you learn from the beach is the power of nature. So I've been out in the surf several times with people who have not been able to swim back in. I remember one particularly ill-conceived midnight skinny dip in hurricane-stirred waters on a remote beach, where I realized after we'd been stuck out there for a while that I was probably a strong enough swimmer to get back in, but my companion might not be. And there was no one who could save us. It was dark, there was no stronger swimmers on the beach, and we were too far from any rescue. So it was up to us, and after what felt like an hour, but was probably less, of being hit in the face by waves that we couldn't see and making zero progress towards shore, the thought flitted through my head, at what point do I swim in alone? And it is my enormous relief that my immediate response is there is absolutely no way in any world that I am ever swimming in without my friend. But believe it or not, astrophysics actually helps you even in those sorts of situations. I'm pretty calm about the idea of being recycled. I see myself as one part of this sort of intricate whole that is the entire universe. I'm going to play my role, and I'm going to pass away, and the universe is going to be changed slightly because of my presence here. I think it's actually very reassuring to think about the fundamental interconnectedness of all things, if you let me borrow a phrase from Dirk Gently's Holistic Detective Agency, one of Douglas Adams' non-hitchhiker novels. Some fans in the audience. So Dirk Gently, his motto was the fundamental interconnectedness of all things. That's how he did his detecting. He said that he used to navigate by following the car that happened to be in front of him on the road. He said he rarely got where he intended to go, but often ended where he needed to be. Now, I'm not advocating that you throw away your smartphones and start navigating by karma. However, the interconnectedness of the systems of the world is just so starkly apparent when you study space, when you study the life cycles of planets, of stars, of galaxies, that you can't help but feel a part of that intricate whole. Now, for the last 7 years, I've been involved in a research group that is trying to measure the distribution of galaxies in the universe. We're looking for patterns. And the reason is that the distribution of galaxies isn't actually random. And the reason why is really interesting. If we started from a Big Bang, and then that means that all of the observable universe that we can currently see was once packed into a tiny volume. Now, if you were to live back then, like back 100,000 years after the Big Bang or something like that, it would have been like living in the interior of a star, except a star that extended in all directions as far as you could go. Now, these days, sound doesn't travel in space because it's a vacuum. But go back then, it was really dense. Sound was traveling everywhere. And light couldn't travel very far because as soon as light got emitted, it got absorbed by something else that it hit. So it's sort of like living in a fog. But all things come to an end. And as the universe expanded, the gaps between the particles became so large that when the sound waves compressed, they couldn't find anything to bounce back off. And at that point, these sound waves ended up sort of getting frozen in. So you had these dense spots that stuck there, and beside them slightly emptier spots. And the light from that time could travel because now the universe was empty enough for light to be able to propagate. Now, if that light was propagating, it should still be here today. And we've actually been able to see it. It's known as the cosmic microwave background because it's in microwaves. It was first seen in the 60s, but this is the latest picture of it that was taken by the Planck Space Telescope, and this was released last year. Now, looking at this microwave background is sort of looking at a billiard ball. It's very, very smooth. But if you took a microscope and looked at the billiard ball, you would see sort of like peaks and troughs and humps and texture. Well, this is the magnifying glass version of the cosmic microwave background. What you're seeing there are hot spots and cold spots that correspond to sort of peaks and troughs of those sound waves in the early universe. And it might look sort of messy, but there's actually a characteristic size to those hotspots, those overdensities. Now, if we start with something like this in the early universe, we can calculate what is going to happen. And I could do some pen and paper here for you, but I think that would be quite boring. It's much more exciting to chuck it into a supercomputer and see what happens with that. And it's much more accurate as well. So here you see a portion of the universe that has been expanding. It starts out very smooth, but over time, little bits that were a bit more dense than the rest sucked material in due to gravity. And over time, those bits that started over dense are the bits where galaxies form. So long story short, we expect that we should be able to see an imprint, a sort of periodic pattern from the sound waves in the early universe in the distribution of galaxies today. That sounds a little bit crazy, but after 5 years of observing effort with a team of about 30 people here in Australia, we were able to analyze the data, and that pattern is exactly what we saw. It's really astonishing. So it's a sign of the fundamental interconnectedness of all things, I think, that the same equations that I used to describe waves on Coogee Beach are the same equations that tell me how waves propagate in the really early universe. And the same equations that tell me what happens to the pressure when I pump up my bike tire are the same equations that tell me how fast sound waves should travel and what pattern they should be there. And the same equations that tell me how far I should be able to see through fog tell me that there's a limit to how far I should be able to see back in the early universe, and that cosmic microwave background should be there. And the same equations that govern where I should move to what happens when I throw a basketball are the same equations that govern how matter moves and falls into galaxies and where galaxies form. And all of that same physics is the same physics we use to build digital cameras, build enormous telescopes, build rockets that can launch telescopes up into space, do the radio communications that can talk to those telescopes and get the images that they take back down to Earth. And when we use all of that technology, look up at space and observe the galaxies and this microwave background, we see the patterns that we expected to see. I think that's really amazing. So the reason that we've been able to do all of this is because of the power of digital cameras on enormous telescopes. This is a picture of empty space. This is what you get if you take the Hubble Space Telescope and you stare at a blank piece of sky and you leave the shutter open for 11 days. What looks like a blank piece of sky actually appears full of faint galaxies that were just too faint to show up in your previous images. The most distant galaxy in this picture emitted the light that we now see more than 12 billion years ago. Now, put that in perspective. This formed 4.5 billion years ago. So if we think about how this works, this distant galaxy over here, it emits some light. Meanwhile, over here, some supernovae are going off, some dust clouds are forming, those dust clouds are collapsing under gravity. On the center of one of those dust clouds, a star ignites. Meanwhile, light is still traveling, light is still traveling. Over here, a disk forms around this star. Planets coalesce on that, sort of from that disk. Oceans form on the planets, little creatures crawl out of the oceans, they learn how to build telescopes. And the first thing that light has hit in that entire time is the mirror of our telescope. It goes to show just how empty space is, how much space there is out there. And when you think about it, it should give you a really profound sense of the importance of this little tiny strip of atmosphere that we have on our precious little planet here, and how important it is for us to look after that, because it is so difficult to get somewhere else, and there is so few places that we could possibly go to if we wrecked this one. Did you know that the emptiness of space is also demonstrated by galaxies? Did you know if you took two galaxies, like the Milky Way and Andromeda, they're going to collide in about 4 billion years. If you smash them directly together, that there is so much space between the stars that they almost pass directly through without any star-on-star collisions. The space is really empty. Now, this is a picture of Earth. It might not look like the normal sort of Earth picture that you would usually see, but that's because there's a big fat Saturn in the way. That's Earth there. Can you see it? This is one of the most distant pictures of Earth ever taken. This is the most distant. Can you see it? That was taken by Voyager. Now, Voyager recently became one of the first human-made spacecraft to leave our solar system. It took it 37 years to get that far. It is hard to get into space. We sit fragile little humans atop these enormous rockets like the brave souls on Challenger. We think of ourselves as a space-faring race now, but no one has been to the moon in my lifetime. And that's just the moon. In terms of space, that's like shifting on your seat. That's nothing. But despite the difficulty of getting there, we can learn so much by studying it. Now, we have heaps of challenges left to discover, things like, dark energy and dark matter. But it's always important to remember just how far we've come. Now, we see dark energy and dark matter by watching how galaxies move. It's sort of like trying to figure out what the wind is by watching the leaves of trees move. If you think about it, 200 years ago, or a few hundred years ago, we didn't actually know what wind was made of. We didn't have a particle theory of matter. We didn't have the periodic table. We didn't know what oxygen and nitrogen were. We've come a long way in that time. Maybe it'll take another 200 years for us to figure out things like dark energy and dark matter. Who knows? But who knows what we're going to be able to do once we figure them out. Now, one thing that I do know is that one of the reasons we've come so far is because humans looked up and wondered. So I surely hope that you have had a wonder-filled day.